Okay, so I needed to go through this in order to finish off the basics of telescopes before we move on to something else. The key thing that we're going to talk about here is known as the Rayleigh Criterion. I think that's the name it appears under your data sheet under. So, but what we're really talking about is the fundamental limitations of telescopes, the things that limit telescopes that are fundamental to and would be limiting the telescope, whatever the design. So, aberrations depend upon the design. So you can reduce the aberrations, and so they're not fundamental. You can find a way around a lot of the aberrations. The kind of things I mean by more general limits that are fundamental are things like collecting power. Collecting power is just the amount of light that's going to enter your telescope, and that just depends upon the aperture of your telescope. It depends upon the area of the aperture of your telescope, and therefore collecting power is proportional to the square of the diameter, or the square of the radius. But usually when this turns off, it's the square of the diameter they ask you to talk about. So collecting power is a fundamental limit on a telescope. The collecting power wouldn't be affected on whatever design of telescope we use, whether we use refracting, reflecting, Cassegrain, Newtonian. That would be a general fundamental limit. The harder one to understand is resolving power. And resolving power is the ability of a telescope to separate two objects. Now, what do I mean by that? Well, to sort of give you an example, but it's not quite right. If the light from two objects fell on the same pixel, if the spacing of the pixels was quite large, light from two objects falls on the same pixel, then there's no way the telescope can tell them apart. But that's not fundamental, because that depends on the CCD design. You could sort that out by having pixel elements that were closer spaced on your CCD. So that's not fundamental, but it sort of gives you the idea of what I mean by being able to resolve. Can I tell two objects apart when I look at the image that my telescope creates? So the more fundamental version of the same thing is when the optics of the telescope causes two objects that should be points, we talked about the fact that stars should be absolutely narrow, sort of almost infinitely narrow points, to spread out and overlap. So if two objects that should be points spread out and overlap so much that we can't tell the two of them apart, then at that point we're at the telescope's resolving power. Now, what's causing the objects to spread out on the CCD? Well, of course, it's single slit diffraction. Now, I know that seems crazy. You're thinking to yourself, but we talked about diffraction in terms of the wavelength being the same kind of size as the aperture. And here he is talking about the aperture of a telescope affecting the, producing a diffraction pattern, when the aperture of the telescope might be 10 meters across and the light is only 0.5 of a micron across. They're not even close to being the same order of magnitude. They're 7 orders of magnitude between them. How can that possibly be producing a diffraction pattern? Well, the answer is it's only producing a very slight diffraction pattern. When we're talking about what are the absolute fundamental limits that are preventing a star from being able to be resolved from its very close neighbour, then that little tiny bit of diffraction that can be produced just by the light entering the aperture of the telescope is enough to spread the light out enough that the two might overlap. And a bit later on, I'll give you an example of some of the numbers involved here, and you'll perhaps get an idea of the amount of diffraction we're talking about is absolutely tiny. But it's enough diffraction to put a fundamental limit on the ability of telescopes to tell stars apart. So that was single slit. Of course, what we're talking about is light coming through a circular aperture. And here you can see laser light going through a relatively small hole, and you get the central peak where the laser light gets spread out by diffraction, and then you get side peaks that correspond to that single slit diffraction graph that we were looking at before, and the side peaks make concentric circles. And so I've got a couple of images there of that. And this disc with a central bright area and then faint side fringes, circular side fringes, has a name. It's called an airy disc, and you're expected to know that name for your exam. Right, now this is a graph. The only difference between this and the graphs that we looked at when we were doing it, and you might have spotted it on the graph I showed you earlier on, but I forgot to mention it, is that this axis is angle. When we've drawn single slit diffraction peaks before, that's been distance. This time it's angular separation that's on that axis. This axis, of course, is intensity. So I've got the peaks from two stars. Those two stars should be just individual points, should be almost infinitely narrow spikes on my CCD. The reason they aren't, the reason that the central peak has been spread out, and then the reason there are side bands, is because the light has diffracted very slightly when it's entered the telescope. Now, if the angular separation between the stars is quite large, they'll start to overlap. But these side fringes overlapping will mean you've got a bit of a mess in between the two of them when you're looking at the light, but you can still clearly see star 1, star 2. You can still resolve the two stars apart. So we've not yet reached the resolving limit for our telescope. However, if I move them closer still, I learned that trick from Mr. Smith. If I move them closer still, this point here is regarded as being the point where you cease to be able to tell them apart. You think, I can still see them too. But if you think about the light adding up from those two, we've got that much light. Oops, I'm on the wrong pen. That much light from each of them, which means that it will come to there when I've got the two of them added together. And so those two peaks are very much overlapping and become essentially a single blob of light, maybe with a little bit of brightness one side and the other, but essentially they become a single blob of light. And they do that where the peak of this one, see the peak there, peak of this one lines up with the peak of the first fringe of the other one. Okay, so that's what that red line I've just drawn is indicating. Peak of one lining up with the first side fringe of the other. So there that is written out. Two stars will be indistinguishable when the peak of one corresponds to the first side fringe of the other. So this then is the minimum angular separation that we can have between a pair of stars. Angular separation between that pair of stars goes even slightly smaller than that. Can't tell the two stars apart. Angular separation goes slightly bigger than that. Providing everything else about the telescope is perfect, then we can tell the two stars apart. So this represents the absolute fundamental limit of the operation of telescopes. And it's called the Rayleigh Criterion because Rayleigh worked it out, and criterion is the singular of criteria. So it's the one criteria that determines how well telescopes work. There you got the description of it there. Fundamental limit on the ability of a telescope to resolve two stars occurs when the first side fringe of the airy disk resulting from diffraction of the light into the telescope's aperture of one lines up with the central maximum of the other star's airy disk. So you have to learn that definition, you have to learn that terminology, airy disks. Now, the proper mathematical answer for when that occurs is when the angular separation between the two in radians is equal to 1.22 multiplied by the wavelength divided by the diameter of the telescope. And you will, if you use that formula in an exam, get the marks for it. Where it's turned up in this latest specification, that's always been available as an alternative. But for reasons, I don't know, our course uses an approximation. So our course leaves out the 1.22, doesn't go in there. This would be true if they were single slits rather than circular apertures, apparently. But I don't know why our course leaves out the 1.22, but it does. So if you looked up the Rayleigh Criterion in your data sheet, you would see this second equation. You wouldn't see the 1.22. Oh, fair enough, they made it easier for you. But the key thing for you guys is in radians. So angular separation. Angular separation in radians. Given by lambda over d. So this is the minimum angular separation. Now this is peculiar in and of itself because we're calling this resolving power. And usually power is better if the number's bigger. Collecting power is better if the number is bigger. Resolving power is better if the number is smaller. Yeah, we get a better resolving power the smaller that is, because the smaller that is, the closer two stars can be in the night sky, and I'll still be able to separate them in our telescope. So resolving power is a peculiar one, in that it's sort of backwards. And I've seen guys write answers to exam questions that make it clear that they haven't understood that, and they've been confused by that. So, yeah, another one to try and get down, maybe in your own notes that you're making about this, you're going to sort of put that in highlighter or something, that really a better resolving power is a lower angular separation. I perhaps should have written it out on here somewhere, and I haven't done. Okay, let's have a look at an example question. It's proposed to examine Neptune's largest moon, Triton, with an optical 5-meter telescope. If Triton is 2,700 kilometers across and at its closest is 29 AU away, comment on the likely success of this endeavour. You can tell I wrote that, can't you? Likely success of this endeavour, definitely me. Now, a couple of things to unpick here. AU to begin with. That stands for astronomical unit. It's the distance between the Earth and the Sun. And it turns up in quite a lot of exam questions, it just turns out that Neptune is 30 AU. So the Earth is 1 AU and Neptune's 30 AU. None of the rest are nice even numbers like that. It's just Neptune and the Earth. And of course, if the Earth itself is 1 AU away from the Sun and Neptune is 30 AU away from the Sun, then the distance between the Earth and Neptune, the minimum possible distance between the Earth and Neptune, is 29 AU. So hence that distance. AU again is on your data sheet. You can look it up, its value in meters on your data sheet. I just happen to know the number. And that's in kilometers. Got to pay attention. That's in kilometers on your data sheet. That will be in meters, but that's in kilometers. Now, we're also, because this is astro, going to be using the small angle approximation here. So what I want to know is, what is the angular separation of one side of Triton compared to the other? Okay, what's the angular separation of either side of Triton in my telescope? And then I'll compare that with the resolving power of the telescope, and I'll be able to work out whether or not my telescope is good enough to do the job. So, to work out the angular separation from either side of Triton, there's Triton, there's its distance away, 29 AU, and we know this is 2700 kilometers. I don't know why I've just written kilograms. Kilometers. Come on, Dr. Cook. Okay, now you're thinking I need to use some trigonometry to find out what this angle is. I'm going to tell you no, you don't, because we're going to use the small angle approximation, and I'm going to go into the small angle approximation in more detail in the lesson, in the live lesson this week. So no, you don't need to do trigonometry because we're going to use the small angle approximation. Because the small angle, if this was a circle, if that was a curve there, then the length of that arc would be given by, so the length of the arc would be given by r theta, where that's theta and that's r. Now, because that angle is so tiny, The difference between that being a curve and that being a straight line is utterly negligible. So we can work out our theta from that equation, even though that equation actually describes a curve and the diameter of something is a straight line, because we're applying small angle approximation. So we're going to end up with theta is equal to L over R, which is equal to 2,700 kilometers divided by, now, 29 AU. And I just happen to know, you'd have to go to your data sheet, that 1 AU is 150 million kilometres. Okay, so that's our sum. That will work out theta in radians. And it turns out to be, oops, it's a bit annoying that I've drawn over it, turns out to be 6.2 times 10 to the minus 7 radian. Now, you get an idea that this diffraction that we're talking about as the light enters the telescope is not big. 10 to the minus 7 radians. So this is the angular separation. Okay, that's the angular separation of one side of the Triton compared to the other side of the Triton. Now, we also need to work out what is the best resolving power of the telescope. So, took me scribble off there. What's the best resolving power of the telescope? And that's given by lambda over d according to the approximation that we use in our course. Now, you're expected to know this, roughly what order of magnitude is visible light. It doesn't tell you in the question. You're expected to know. So green light, about 550 nanometers. So 550 times 10 to the minus 9. If you'd used 600, you used 500, you'd still get the marks. And then it's a 5 meter telescope, so that's 5. And that gives us 1.1 times 10 to the minus 7 rads. So now we've got some numbers, we can answer this question. The angular separation between the two sides of Triton is 6.2 times 10 to the minus 7. The best resolving telescope power of our telescope is 1.1 times 10 to the minus 7. So clearly our telescope is capable of resolving Triton. Our telescope will see Triton as a disk. So that's all good. But it says examine in the question. Are we really going to be able to examine Triton? This is roughly a fifth of that. So all we're going to be able to see on Triton from Earth using our 5 meter telescope is we're going to be able to see features that are about the fifth of the diameter of Triton across. So, you know, if it were the Earth, we'd be able to see that North America was a splodge compared to the Atlantic and the Pacific, and that were different coloured splodges. That's what we'd be able to see. So examine. I'm not convinced we'd be able to examine anything with this telescope. I think if we wanted a good look at Triton, we're going to have to use bigger than a 5 meter telescope, or we're going to have to send a space probe. Because examine, being able to see something that's a fifth of the total diameter of the thing is not examine. And so that's my answer. The telescope should be able to resolve features on Triton that are the size of about a fifth of the moon's diameter. You know, if that's all you need in order to get your PhD, as the first ever decent pictures of Triton, then woohoo, you get your PhD. But chances are somebody's already got better pictures than that, and you ain't going to get your PhD based on that. Okay, does that make sense? That's a relatively typical question. As I say, we'll do more on the small angle approximation in class. AU will come up again and again and again, so you'll get used to them. And you know, it's just this idea, when students get this kind of question, what we commonly see is, the resolution of the resolving power of the telescope is less than you need in order to be able to see it, therefore they can see it, woo, done. And they're not stopping to think that actually, yeah, you're going to be able to see it, but you ain't going to be able to see it very well. And it's that extra bit of stopping and thinking that's going to get you the better grade. Okay, in summary, what have we talked about? I've said there are two fundamental limits on a telescope's performance. They are collecting power, which is proportional to the area and therefore the diameter squared, and the resolving power, which is the smallest, not the largest, the smallest angular separation that can be resolved. It's measured in radians, it's given by the Rayleigh Criterion, and it's improved by increasing the telescope's diameter, so we get less diffraction. It's also improved by using shorter wavelengths, so we get less diffraction. So sometimes exam questions turn up where they ask you to compare sort of the resolving power in blue compared to the resolving power in the infrared. And of course, the resolving power is better in the blue because lambda is smaller. In your equation there, lambda is smaller. So you get a better resolving power in blue. In truth, of course, if you're using a telescope, you don't get a better result in blue because blue light is scattered by the atmosphere. And so you get a slight blurring in blue because blue light gets scattered. So that, you know, when you're designing telescopes, when you're thinking about doing astronomy, it's all these compromises that you have to make. What gives me the best resolving power? But that's the best resolving power on the telescope. What about the atmosphere? The light's got to come through. Okay, so some numbers in there. First, sort of problems that are really like the kinds of problems that you get in the A level, and so relatively simple stuff, but there's quite a lot of thinking involved. To say, if you've misunderstood resolving power and you think it's got to be a bigger number, you won't get any marks. All right, that'll do for now. I will see you in lessons.